So welcome to tonight's webinar for CIS 205. Tonight we will be covering CompTIA's Network Plus exam number N10-005. And tonight's topic is Objective 1.3. And that objective is to explain the purpose and properties of IP addressing. Yeah, I can speak. So tonight we're going to be covering IPv4. By the way, from here on out, I'm going to just try and say IP instead of IPv4 addressing. Then we will be discussing the difference between IP and IPv6 formatting. We'll be discussing the MAC address format, which is actually not really an IP issue, but it's covered under this objective. We will be talking about subnetting, and then we'll talk about the difference between unicast, broadcast, and multicast. And the final discussion will be on APIPA addressing. Excuse me one moment. Sorry about that. So we begin the discussion with IP. So what it is. IP is strictly involved with the third layer of the OSI model. That is the network layer. IP is a 32-bit addressing scheme, and it's broken into 4 sets of 8 bits. And what you see there right below that line is a representation of an IP address. Usually when you see it written out, it's represented in dotted decimal form. And the 192.168.0.1 is exactly what that set of ones and zeros above represent. This style of IP uses class addresses, or at least it did in the beginning, and those classes were A through D. Actually, there's more than that, but you don't need to know that, so we're only going to cover A through D. And how you differentiated the different classes of IP address was through the use of a subnet mask. And we will talk about that some more here in just a little bit. So let's talk about classes of addresses. So a Class A address, the first octet, and the first octet is the first set of, or the first digit to the left, can be any number. Actually, I put down there 1 through 126. It can actually be 0 through 126. And in its binary representation, the first digit on the left is always a 0. And a Class A IP address, the subnet mask is always 255.0.0.0. Now a Class B, okay, so the first thing that you need to know, Class A, with that first octet, or with that first subnet mask being 255, means that that is the network portion. And that means that there are 2 to the 8 possibilities of networks. Essentially like 16,000, I do believe. And the rest of the digits that fall under the 0.0.0 could be used for individual node addressing. That's a lot of individual nodes. Those were used for extremely large networks. I do know that in the beginning, Boeing was one of the entities that actually purchased a Class A network. And they're probably one of the few entities still around that needs a network that large. Now, Class B addresses, they fall within the address range of 128 to 191, and in their binary representation, the first digit is always a 1, the next digit is always a 0. And their subnet mask is 255.255.0.0. And that means that you had 2 to the 16th power networks available, and each of those networks had 2 to the 16th power of network nodes that were available. And actually, that's kind of a misnomer. They had 2 to the 16th power minus 2 nodes available. If you get into advanced addressing schemes, that'll become a little bit more apparent. And actually, I think Network Plus does cover that in some of their stuff. Class C, their address range was always 192 to 223. And their binary representation, the first 2 digits were always 1, the third digit was always a 0. Their subnet mask was 255.255.255.0. And that means that there were 2 to the 24th power networks available, and each of those networks had a possibility of 255 hosts. Much more useful for smaller networks, so on and so forth. But a whole bunch of Class C networks were available. Now, Class D address. Their first octet can be anywhere from 224 to 239. And their binary representation, the first 3 digits on the left were always 111, followed by a 0. And Class D addresses are usually only used for multicast networks, and we will be talking about that here in just a little bit. Okay, so public versus private addressing. The advantages of a public IP address is that it is routable. And usually you only find those on the outward-facing point of a router, because they are routable. Everybody can see them. Anybody can send packets to them. The problem is with public IP addresses is it severely limits the ability of the internet to grow, just because there are so few IP addresses available. So the way to fix that, they created private IP addresses. These are inward-facing, local networks usually. They are non-routable. You can try and route one of these addresses out to the internet, and the router will just bounce it. These addresses never leave the local network. There are 3 private IP addresses ranges, and you need to know these for the Network Plus. There is the Class A private addressing scheme, and as you can see, that's the addressing range is any network that falls between 10.0.0.0 through 10.255.255.255. And actually, if you had a network address like that, that wouldn't work, but that is still within the range of valid IP addressing for a Class A private address. Class B was a little bit more restricted. Its range was 172.16.0.0 through 172.31.255.255. And finally, there's Class C. Private address range, and that's 192.168.0.0 through 192.168.255.255. Now I'm going to give you guys a tip here, something for you to remember. One of the things that CompTIA likes to do is kind of a trick question. What they'll do is they'll ask you to identify the valid private IP, the correct private IP addresses. And every once in a while they'll throw in one like 172.32.0.0, and you need to realize that 172.32 is incorrect. All or they will throw in like 192.169 or 192.167. Just so you got to know these address ranges when you go to take the exam. The advent of private IP addresses has essentially been why the internet has worked for as long as it has and why it took so long to run out of IP addresses. With the advent of the private IP addressing scheme, it really made things easier on the internet and the growth of the internet. And we will talk about that here again a little bit more. So now let's talk about, we've talked about classes of addresses. Now let's talk about classless addressing and why we should be thinking about classless addressing. The first thing is that classless addresses actually slow the growth of routing tables. The larger a routing table grows, the slower a router performs, the slower a network goes. Classless addressing actually eases the pressure on routing tables. And also removes some networking limitations. It allows for some contiguous network routing. That's a little bit of an advanced subject for this topic, but I'm throwing it out there anymore. And it allows more opportunity for growth. It allows for a whole lot more flexibility. When we're talking about classless addressing, we are talking about CIDR, CIDR, which is classless interdomain routing. So let's say you had a network. You had the 192.168.0 network. That allowed you to have 255 hosts. So let's say you didn't need that many hosts, but you needed 2 networks. Well, by using CIDR, you could subnet that and break it in half. And what I mean by that is you could take and you'd write it down 192.168.3.1, and I'm going to pick, oh, and that's wrong. I've got a wrong slide. What do you know? It should be .128/25. So that is a correction I need to make. That's a .128/25, and that means that previous address of 192.168.3.0 is now split in half, and the second half would be represented here by this subnet mask. You'd take and give it a subnet mask of 255.255.255.128, and that would break that single network into 2. You can also, it's not just taking one address and making more, you can actually go in the other direction as well. Normally, 192.168.3.0 is a class C, and that would be in CIDR a /24. You can actually go 192.168.3.0/23. That's a little bit more difficult. That's called super netting, but it can be done. So you can go both ways, but the most common reason is because you are subnetting, breaking down the network, not building one up. So now let's talk about the difference between IP and IPv6. As I mentioned earlier, IP is 32 bits. It's represented in dotted decimal, 4 sets of 8 bits. And there are 4,294,967,296 addresses, individual addresses available using IPv. No, that's not a whole lot of things. Originally, that seemed like that was going to be plenty, but then they realized actually back in the 90s late 90s, but it wasn't going to be enough, so they started working on the fix for that. And they came up with IPv6. Actually, they came up with IPv5 first, but even at that point in time, they realized that it was not going to work. So they moved on to IPv6, and that is a 128-bit addressing scheme. So it's 4 times as large, at least bit-wise. That's a lot of stuff. It's represented by colon-separated hexadecimal. So you have 8 sets of 32 bits. Each set is separated by, and that's in hexadecimal, and each set is separated by colons. Now, how many addresses does it support? Well, it supports over 340 undecafillion IP addresses. That's a lot, if you are wondering. That's 3.4 times 10 to the 38th power worth of individual addresses. That's enough addresses that every device that can possibly connect to the internet, every device, can have its own IPv6 address. And every device that does connect to the internet, I do believe anymore, does have its own IPv6 address. And that means any object can be connected to remotely if you allow it. In IPv6, every device actually gets 2 addresses. They get a global address and they get a local address. And I'll talk about local addressing here in just a moment. Another formatting difference between IPv6 and IP. In IP, the loopback address begins 127.0.0.1. Well, in IPv6, your loopback address is ::1. That is your loopback. So if you need to test your IPv6 stack, you would ping that ::1 address to see if your IPv6 was actually initialized. And what that ::1 represents is that there are 127 zeros in front of that 1. Pretty simple. So now we're going to talk about some other formatting tricks with IPv6. So since it's 8 sets of hexadecimal, that's a lot of digits. They said, wow, that's going to be kind of tough for people to remember. So they said, okay, in any set of hexadecimal, in any of the 8 sets, all leading zeros can be dropped. So this top address, this FE80:001, yeah, so on and so forth, if you drop down to the next line, all the leading zeros have been removed. Then they said, well, what happens if we have groups of zeros? If you look towards the middle of that IPv6 address, you will see that there are 8 zeros in a row. Well, in cases like that, you can drop all the zeros and put in a double colon. But you can only do that once. And they have to be consecutive groups of 0. So when you go to break it down, if you're doing it manually, take care and caution. This FE80 address, by the way, is a local address. That is not routable. It will never leave the network. That is an example of a local IPv6 address. So if you see an address that starts with FE80, it is local, not global. So now let's move on to MAC. So what is MAC? MAC is Media Access Control. That's what it stands for. It's also called a physical address. It's also called a burned-in address. Every machine that has a connection to the network has a MAC. the MAC has to be unique in each network. So you can have two MACs that are the same if they're in separate networks, but if it's the same network, it's got to be unique. The MAC is made up by a hexadecimal number. It's either 48 or 64 bits. Now, in the MAC 48, which until recently has been the standard, the first 24 bits make up the OUI. That's the Organizational Unique Identifier, is what OUI stands for, and that's the manufacturer's code. The manufacturer is assigned, or was assigned, those 24 bits of data from the IEEE. They did not get to make them up on their own, but they did get to make up the second 24 bits, and that's what makes the address unique. Usually that is the serial number. And since there are over 1 million possibilities in that second 24 bits, chances of having a duplicate are pretty slim on any given network. Well, excuse my dog. For a couple of reasons, MAC 48 has fallen out of favor. Personal opinion is because the IEEE, which is the governing body, could not copyright MAC 48, but they did copyright the MAC 64. And since they are the governing body, things are moving to the MAC 64. It operates exactly the same way as the MAC 48, except for it uses 64 bits instead of 48. And it's trademarked by the IEEE. So now let's talk about subnetting. So what is subnetting? That's the breaking up of a single IP address range into separate and independent networks. And why do you want to do that? Well, because it's more efficient and there's less wasted addresses. If you have two routers that are connected together, do you really want to expend an address range that involves 255 individual addresses when you could actually just use 4? And the reason you have to use 4 is 1 is the network number, 2 are the nodes, and 1 is the broadcast. All networks have to have a broadcast address. But it's much more efficient. So here we go. How does it work? So you have a 192.168.0.0 network /24 CIDR, and you want 2 networks. Well, so currently your address range is 192.0.0 through 192.168.0.255. And now you need 2 separate networks. So what you do is you change the subnet mask. So when you break it up using subnetting, 192.168.0.0 /24 actually becomes 192.168.0.0 /25 with a range of addresses of 192.168.0.0 through 192.168.0.127. The other half of the network becomes 192.0.128 /25. And its address range is 192.0.128 through 192.168.0.255. That's the way it's explained, and now I've got to tell you something that you should be aware of. Let's talk about these 2 addresses and address ranges. Remember back in the beginning when I said when you were talking about the nodes, you had 2 to whatever power -2? Well, here's where it comes into play. So this 192.168.0.0, that's not actually an address that is available. That's actually the network. So the actual first address that would be available in that network would be 192.168.0.1. The other address that's not readily available in that network is the .127. That's the broadcast address. The actual last address that's available would be .126. And the same applies for the range down below. The .128 is the actual network, and the .255 is the broadcast address for that network, so it's not available to be assigned. So the last one that could be assigned would be .254. So that's something to keep in mind when you're talking about IP addressing. So now let's talk about unicast, broadcast, and multicast. So what is unicast? Unicast is one-to-one communication. I want to send a packet from 192.168.0.1, and I want to send it only to 192.168.0.2. That's a unicast. Most information flow is unicast. So what's broadcast? Well, broadcast is one-to-many communication. That's that last address in the range, that .255 in most cases. Well, in most cases that we've been talking about. And so let's say you fire up your PC and it doesn't have an IP address, doesn't know its IP address, and it wants to find out. Well, it will send out a broadcast address. It will send out a broadcast saying, hey, I am Mac blah, and it'll send out its MAC address. I need an IP address. Is there a DHCP server available to give me one? And it sends that out to anybody and everybody on that local network. Now, hopefully the DHCP server hears it and will respond, and they respond back to that MAC address with an IP address for that PC to use. Multicast is kind of like broadcast, but not really. Multicast is one-to-a-few communication, or one-to-a select few communication. And where do you see multicast usually? And that's with routing protocols. If you're running RIP, if you're running OSPF, if you're running EIGRP, you're going to be using multicast. That's how one router finds out what other routers are out there and what protocols they're responding to. Is they send them out on specific multicast addresses, and any router or machine that's listening for that multicast can respond. PCs and individual nodes, as a general rule, will not be listening for that kind of multicast, but that's where you will see it most commonly. So now let's talk about APIPA, and that stands for Automatic Private IP Addressing. It has a specific range of addresses. Again, you need to know these. The range is 169.254.0.1 through 169.254.255.254. And what does it mean if you open up a command prompt and you type in ipconfig /all, and you see this as your IP address? Well, here's another mistake in my slides. I put down that a DNS server is not available. No, that's incorrect. What's not available is a DHCP server, Dynamic Host Configuration Protocol server. and that's the server that hands out IP addresses. A lot of routers have DHCP servers built into them, particularly in the small office, home office setting, and they are what hands out the IP addresses to the PCs. Now, if your machine can't get to one, or there's no router available, or there's no DHCP server available, it will get an APIPA address. What does that mean? That means that you can't get to the internet. That means you can't communicate with a router. You're stuck in that local network, and you can only speak to other PCs that are using APIPA addresses, which usually means that something's broken. So what do? Well, look at the router, and usually that's where you will be able to resolve the issue in a small office, home office, reboot the router, DHCP server comes back up, and voila, you're finished. Boy, and I really feel kind of silly that I messed up these slides. Sorry about that, folks. So now we're coming to the end. How about some questions?
Yeah,
sure.
That last slide to me is a little bit confusing because it says no DNS server, and I thought what triggers a PIPA is no DHCP server or none of the DHCP, a broken DHCP server which refuses to give you an IP address, and so it goes to a PIPA and forms the local address. But also maybe, I guess what you're saying in the slide, also DNS is also not available, or that service is also not available. Is that right?
Because no, that's a mistake. No, yeah. Craig, no. Where I put DNS on that slide, scratch that off, put DHCP. It's strictly a DHCP issue. That's why I said it was a mistake, and I feel bad about putting that on the slide.
I got it, yeah. All right.
And presenting it to. Okay? It's strictly a DHCP issue. It is not a DNS issue. It's just strictly a DHCP issue when you get the APIPA.
I got one other quick question.
Any more? Go right ahead.
Is subnetting and subnet masking, are those kind of different? I kind of get the feeling they are.
Yes and no. Subnetting is the breaking up of a network. The subnet mask is how you do it. So that's a yes and a no. They are different. One is what you want to do. The other is how you do it. Thank you for watching this recording, and we'll just open up the floor.